Okay, so in this video I'm going to take a look at the AS Specimen Paper 1. So let's get started with question 1, looking at some particle physics. So we've got some properties about a positive pion and a proton, and we just need to fill in a few gaps. So the relative charge of a positive pion is +1, and it's the same for a proton as well. It's a charge of +1. Pion is a type of meson, which means it's not a baryon, so it has a baryon number of 0. Proton is a baryon and it's not an antiparticle, so it has +1. The quark composition of a pi plus. So to get a positive charge from a meson, you need an up quark, and a pion is not strange, so the other +1/3 comes from an anti-down. A proton, you should know, is an up, down, giving you an overcharge of +1. Okay, so let's quickly move on. So a positive pion interacts with a proton and a kaon can be produced along with another strange particle as shown. So circle which type of interaction is shown in the diagram. So we've got in a pion we just had this, so it's an up anti-down, going to an up, down. A K plus is an up anti-strange, and then it says this particle produced is a strange particle, which means it contains a strange and some other things. So you can see that in this interaction, strangeness is actually conserved, which means this is a type of strong nuclear interaction there for 1 part 2. Okay, so then it says deduce the relative charge, baryon number and strangeness of particle X. So let's look at baryon number first. So pion has a baryon number of 0, proton is +1, kaon is 0, so X must be X is a baryon. And it's not an anti-baryon. So X has a baryon of +1 to conserve baryon number. On the left-hand side, we've got a total charge of +2, and we've got a charge of +1 currently. So it must be have a charge of +1. So to ensure total charge is conserved, and we know if it's going to have strange quark, that's going to be a strangeness of -1. To have a essentially overall strangeness, that's going to be -1 there. Okay, so that completes that one. Let's move on. Particle X can decay to produce a neutron and a positive pion as shown in this equation. Circle the type of interaction shown in this equation. So before we had particle X, which had strangeness of -1. Neither of these two things are strange, therefore this is an example of weak nuclear interaction, because strangeness is conserved during strong and decays are caused by either strong or weak, nothing else. So let's put that into words. Okay, and that's what we've got there, explaining it in terms of strangeness. Okay, so moving on to part 6. The neutron and the positive pion will then decay. The positive pion can decay into a positron and an electron neutrino. Write the equation for this. So we've got a neutron to start with, and we're producing we're going to produce a beta minus particle, because remember we're producing a proton, so we need the charges to cancel out, and now we need to make an anti-electron neutrino. So then it says explain why no further decays are going to occur. So we've got, as part of this, 2 fundamental particles, electrons and neutrinos, so those aren't going to decay, and proton is the stable baryon, or the most stable baryon, so again that's not going to decay either. So let's get that down. Alright, so that would be my explanation there. Let's swiftly move on to question 2. So we are going to have a look at the photoelectric effect. So we can demonstrate that using ultraviolet light and certain types of metal, and we can show that the plate loses charge. So explain why when ultraviolet light is shone on a positively charged plate, no charge is lost by that plate. So this is essentially kind of asking you about the stopping potential experiments. So if you were to shine the light onto the plate, the electrons would be emitted, but the plate is positively charged, and if you remove an electron it becomes more positively charged. So although the electron tries to escape, it's attracted back to the plate, and therefore it's not actually going to end up escaping. And as I said, that's basically what's going on with stopping potential. Alright, so that would be my explanation there. So the threshold frequency and the work function are important ideas in the study of the photoelectric effect. Tables 2 and 3 summarize the work functions of 3 metals and photon energies of 3 UV light sources. Discuss the combination of metal and UV light source that could best be used to demonstrate the idea of a threshold frequency and the idea of a work function. So to demonstrate a threshold frequency, what we really need is to pick a material and then shine light of different photon energies or different frequencies on it and show that only above a certain frequency or energy that electrons are emitted. So because we've got these ranges of energy, we could actually pick any of the materials. So if we picked zinc, for instance, we would see that for light source 1 we'd have no emission, and then for 2 and 3 we would, theoretically. For iron it would be emitted with 3 but not with 1 or 2, or with copper it wouldn't be with 1 or 2 and we could with 3. So we could pick any of the materials for this, and what we're going to do is change the light source on them and see that only certain light sources will actually cause an emission. Okay, so that would be an explanation of how to demonstrate the threshold frequency. So I'm halfway there. So over the page, let's look at how we could demonstrate work function. So to demonstrate work function, I am going to essentially use the same light source every time now, and essentially by changing the material, we'll see that some of them lose charge using the same photon source, some of them do not, which gives us the idea of the work function. So what we need to do is decide which light source we would use. So we are going to need to use light source 2, because if we use either light source 1 or light source 3, the same thing would happen for all 3 materials if we use those. 2 is the only one that's going to show a difference, so I'm going to pick light source 2. Okay, so that's what we've got. As a result, we're going to find zinc loses its electrons, but the other 2 materials won't with source 2, because the photon energy is greater than the work function only for zinc. So we can see that the work function is a thing. Okay, so let's move on to part 3. So part 3 wants us to calculate the maximum kinetic energy in joules of electrons emitted from a zinc plate when illuminated with ultraviolet light. So this is the equation we are going to be using, relating photon energy, work function, and the maximum kinetic energy. So we want to find max kinetic energy. So we're going to do 6.63 times 10 to the minus 34, because that is your Planck's constant there. The frequency is 1.2 times 10 to the 15. So now we've calculated our photon energy. We need to subtract the work function, but in joules. What am I doing? Which is 4.3 times by 1.6 times 10 to the minus 19. So if I grab el calculatore, it comes out as 1.076 blah blah blah. So that's essentially 1.1 times 10 to the minus 19 joules, once you round it to 2SF, which would be appropriate for this question. So then it asks us to explain why your answer is a maximum. So in that calculation, we've assumed the electron is on the surface of the material. If it's below the surface, some of the photon energy is transferred to move it to the surface, resulting in a smaller maximum kinetic energy. Alrighty, and that's completed question 2. So let's move on to question 3. Okay, so we've got a diagram showing a version of Quincke's tube, which is used to demonstrate interference of sound waves. So we've got a fixed side over here and a movable side over here. So it's a little bit like a trombone, I guess, because we can extend or move in this movable part. And we've got a loudspeaker at X, so at the top, and it produces one frequency or one wavelength or whatever, and sound all travels at the same speed, so essentially we've got all those things the same, and the sound waves enter the tube and the sound energy is divided equally before traveling along the fixed and movable tube. So half the energy goes this way, half the energy goes this way. Two waves superimposed are detected by a microwave at Y. The movable tube is adjusted so D1 equals D2, and the waves travel the same distance between X and Y. And then as the movable tube is pulled out, the sound wave gets quieter and then louder. Explain the variation in loudness of the sound at Y as the tube is pulled out. So when D1 equals D2, the sound waves travel exactly the same distance, so they meet in phase, or have a path difference of 0. So you're going to get a maximum formed when those two superpose. Then as you extend D2, you're going to get to the point where the path difference is equal to a wavelength over 2, and you get them in antiphase. So that's where you get the quietest sound, and it's going to decrease down to that point. And then as you increase the D2 again, you get back to a path difference of lambda, which means they're back in phase, which is why it gets louder again. So let's put that down. So that's the first part. Now let's explain what happens as we increase D2. So then as we increase D2 and the path difference equals half the wavelength, we get destructive superposition, producing the quietest sound. And the final stage is we continue to increase the path difference up to being equal to 1 wavelength, and that means it gets louder again. Okay, and that would round off the answer. Let's move on to 3.2. So the tube starts in the position shown in figure 1, so with the distances equal, calculate the minimum distance moved by the movable tube for the sound detected at Y to be quietest. So essentially we need to move it so the path difference is equal to lambda over 2. So let's first work out what the wavelength is. So wavelength is the velocity of the wave divided by the frequency. So that's 340 divided by 800. So let's work out what that is. So 340 divided by 800, which is 0.425 there. So the path difference needs to be equal to lambda over 2. So lambda over 2 is equal to that answer divided by 2, which is 0.2125. So if we look back at the diagram, we need to think about how the actual total distance traveled by the sound wave changes. So if you look at the diagram, you can see that as you increase D2, that has double effect on the length of the path, because you've got two sides where essentially lengthening on the square. So actually we need to divide our final answer by 2 to work out what happens to to find out actually the actual distance we need to stretch it, which means we get a distance of 0.10 meters. And just to reiterate, so extending D2 increases 2 sides of the shape. So that's why we end up with essentially half of that answer there. So that's the amount we actually need to move D2. Okay, so Quincke's tube can be used to determine the speed of sound. State and explain the measurement you would take to obtain a value for the speed of sound using Quincke's tube and a source of a known frequency. Okay, so we're going to start with the two sides, or D1 and D2, equal to each other, and we're going to increase it until we find a quiet point or a minima, because we know then that the amount we've changed the distance is going to be a quarter of the wavelength, because the path difference is now half a wavelength. And we're going to do that a few times, so they're going to find the next loud one, then the next quiet one, next loud one. So all of those are going to be separated by a quarter of the wavelength, so we've now got essentially repeat readings of our wavelength, and then we can use the frequency and wavelength to get the speed. Okay, so that's our first part of our explanation, remembering that the path difference is half a wavelength, so the change in D2 is a quarter of the wavelength. And then we've got these last two stages explaining how we then get the speed from that. Okay, so let's move on to question 4. So we've got spectacle lenses can be tested by dropping a small steel ball onto the lens, as shown in the diagram, and then checking the lens for damage. So we've got some of the factors of the ball and what height we're going to drop it from. Calculate the density of the steel used for the ball. So first we need to work out the volume of the ball. So volume is 4 over 3 pi r cubed. So that's going to be 4 over 3 pi. And we've got the diameter, which we'll divide by 2, then times by 10 to the minus 3 because it's in millimeters. And then we'll cube it. And that gives us a volume of times by 8 times 10 to the minus 3 all squared, giving us a volume of 2.14 blah 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 times 10 to the minus 6, and that's now in meters cubed because we convert it into meters. And we know that density is the mass divided by the volume. So we were given the mass in the equation. It was 0.016. So 0.016 in kilograms divided by our volume gives us 7,460. So that is going to be 7.5 times 10 to the 3 to 2 SF kilograms per meter cubed. Okay, so that's our density. In the test, the ball bounced back to a height of 0.85 meters. Calculate the speed of the ball just before the impact. So we knew the height from which it was dropped is 1.27. So let's set up our SUVAT. So when it falls, it's going to decrease its height. Well, it's going to be displaced downwards by minus 1.27 meters. When it's dropped, its initial speed is 0. V is what we want to find out. A is going to be minus 9.81 because it's accelerating downward, and the time we don't know. So we're going to want the equation without time in it, which is this one, v squared equals u squared plus 2as. So then we can get rid of u squared because it's 0, so v is going to be the square root of 2 times minus 9.81 times by minus 1.27, and when we do that, let's calculate that. So 2 times 9.81 1.27 square rooted gives us an answer of 4.99 blah blah blah. So that's going to be 5.0 meters per second to 2 significant figures there. Okay, let's move on to part 3. Okay, so then to quickly go through 4.3, because it's essentially the same method as before, we want to calculate the speed of ball just after impact. So essentially we want the initial speed in the upward direction. So we know it reaches a max height of 0.85. We know it ends up at 0 because that's when it matches maximum height. And we know the acceleration is against the motion here. So that's why we've got A equals minus 9.81. So using the same equation, because we still don't have time, we can do the calculations and end up with 4.1 meters per second there. Then if we want the change in momentum, we essentially need the final momentum minus the initial momentum, but remembering momentum has direction, so the sign is important. So the final momentum is going to be the one we've just calculated, velocity after the collision. The velocity going in is 5, but downwards, so it's actually -5. So effectively we end up adding the two velocities together, timesing by the mass, giving us this change in momentum. And then if we've got a contact time of 40 milliseconds, we want the average force. So the average force is going to be the change in momentum divided by the time over which that change occurred. So change in momentum divided by the time in seconds gives you 3.6 newtons. And then explain, with reference to momentum, why the test should specify the material of the plinth the lens sits on. So if it's a soft material, that's going to lengthen the collision, which would essentially decrease the force for the same change in momentum. So let's put that down. Okay, so that's what we've got there. Okay, so that finishes question 4. Let's go on to question 5. So we've got a circuit with a thermistor in it. It's in series with a variable resistor. And we got a graph showing how the resistance changes as temperature changes. So we can see that as temperature increases, the resistance decreases. So we're looking at an NTC thermistor. The resistor and the thermistor make up a potential divider. So it says, explain what is meant by a potential divider. So potential divider is when you have two or more resistors in series so that the potential difference is divided between them. That's what we've got there. Let's go on to part 2. State and explain what happens to the voltmeter reading when the resistance of R is increased while the temperature is kept constant. So if the temperature is the same, the resistance of the thermistor stays the same. So if you increase the other resistor, that's going to make the total current go down. And if you make current go down, the potential difference across the thermistor is going to decrease using Ohm's law there. So, okay, so that would be the answer there. You could also use the potential divider equation to explain exactly the same result. So if you increase the potential increase R, the potential difference across the thermistor would decrease because it's divided in the potential divider is divided by a bigger value, so you get the same thing there. Okay, so then state and explain what happens to the ammeter reading when the temperature of the thermistor increases. So that's basically what I've looked at before. So higher temperature means lower resistance, and lower resistance for the same EMF is going to give you a higher current. Okay, so that would be the explanation for that question. Okay, so let's go on to part 4. So the battery has an EMF of 12 volts. The temperature of 0 degrees, the resistance of the thermistor is 2500. The voltmeter is replaced by an alarm that sounds when the voltage across it exceeds 3 volts. Calculate the resistance of R that would cause the alarm to sound when the temperature is 0 degrees. Okay, so let's just quickly sketch what we've got. So we've got 12 volts going round. We've got a 2.5 kilo ohm resistor. We don't know what R is. And we know the potential difference across here is 3, which means we know the potential difference across here is 9 volts there. Okay, so that's what we know. So using a potential divider equation, so we know that 3 is equal to 12 times by 2.5 over R plus 2.5. This is going to give an answer in kilo ohms for R. So we can rearrange that a little bit. So let's divide both sides by 3, multiply both sides by R plus 2.5. R plus 2.5 is equal to 12 divided by 3 times by 2.5, which is 10, which means that R is going to be 7.5 kilo ohms, because we've had all the resistances in kilo ohms, so that's going to give us an R in kilo ohms. Okay. So one change that you would make to the circuit, so instead of the alarm coming on when the temperature falls, it comes on when the temperature rises above it. So essentially we just need to move the alarm, so instead of being across the thermistor, is now across the resistor in the circuit instead, because that's when the circuit would behave in the opposite way. Okay, so that's what we would do, and if you don't quite follow that, do go back through the same logic we've been through before and see how that works. It's a worthwhile exercise. Okay, so let's move on to question 6. Okay, so if lengths of rail track are laid down in cold weather, they may deform as they expand when the weather becomes warmer. Therefore, when rails are laid in cold weather, they are stretched and fixed into a place while still stretched, called pre-straining. So we've got some data for that. So we've got the Young modulus, we've got the cross-section area, and we've got the amount of pre-strain for each Kelvin temperature that the rail is expected to experience. So a steel rail is laid when the temperature is 8 degrees and the engineer decides to use a pre-strain of 3 × 10 to the -4. Calculate the tensile force required to produce a pre-strain in the rail required by the engineer. So you should know that stress is Young modulus times the strain, which means force over area is equal to Young modulus times strain, which means that force is going to be Young modulus times the strain times the cross-sectional area. So let's do that. So 2 × 10 to the 11 times the strain, which was 3 × 10 to the -4, times the cross-sectional area, 7.5 × 10 to the -3, gives us 4.5 times 10 to the 5 newtons there. Fairly straightforward and a nice easy 3 marks. Calculate the elastic strain energy stored in a rail of unstressed length 45 meters when the pre-strained as in part 6.1. So we need to first find the extension, which is going to be the strain times the original length. So that would be 3 × 10 to the -4 times 44 times 45, which is equal to 0.0135 meters. The energy stored in a stretched material is half Fx. So let's multiply by our answer by 4.5 times 10 to the 5, divided by 2, get 3037.5. So that's going to be 3.0 times 10 to the 3 joules of energy stored there if we use our unrounded answers. Okay, so let's move on to part 3. Calculate the temperature at which the steel rail becomes unstressed. So we've got the strain, remember, is 3 × 10 to the -4, and the strain per temperature change we got given earlier is 2.5 times 10 to the -5. So we can get the temperature change by doing the strain divided by the strain per temperature change. So that's going to be 3 × 10 to the -4 divided by 2.5 even times 10 to the -5. So let's do that. So 3 × 10 to the power of -4 divided by 2.5 times 10 to the -5. That gives us a temperature change of 12 Kelvin. So then the temperature was 8 degrees, so plus 8 gives you 20 degrees Celsius, because we've calculated the temperature change, so we're going to get 20 degrees in the end. Okay, so explain why the engineer does not use the highest observed temperature at the location of the railway track to determine amount of pre-strain. Because we don't spend a lot of time at the maximum temperature. If you think how many days of the year you actually spend at your maximum temperature, maybe 1, 2, tops, especially in the UK, if that's where we're modelling this. So we want to actually reduce the amount of stress experienced by the material in its normal working condition, not at its maximum, so that's why. Okay, so that's what we've got there. We're trying to essentially minimize the average stress that the rail experiences, and that's how we can do that. So that finishes this specimen paper 1. I hope you found that useful to review your answers to this paper. If you have any questions or any queries, please feel free to comment on this video and let me know so I can help clear those up for you. But thank you very much for taking the time to watch.